So, as I mentioned in the previous video, virtually all we know about chemistry comes from the interaction of light or photons with these chemical elements. And so um, we need to jump into that and explore that a little bit. But I think the first thing that we should talk about is the fact that not all light-matter interactions are the same. And you've seen the pictures on the right in your real life probably multiple times. So the image on the left denotes this thing called a prism. So a prism is really just, it's typically a chunk of glass, but it could be a variety of other things that changes the speed of light through the medium relative to its speed through a vacuum. And what that does is it causes different wavelengths of light to move at different velocities. And if you cut the prism like a triangle like this, you can get the light to bend and actually separate. And so if you've got sunlight, what we often consider to be white light, you've got that coming in to the prism here. That white light can actually go through and be separated into its constituent colors. And so it's really important, you probably already know this, but let's really hammer it home, reinforce it. White light or sunlight is actually composed of all of the colors of the spectrum, Roy G. Biv, and those outside of what we can see. Right, because we can only see this narrow band of the EM spectrum, the Roy G. Biv portion. And so a prism can break that apart. The same effect occurs in the sky when you've got sort of a bunch of thin droplets of water. Those water droplets can act just like a prism, and that's why we get these rainbow effects. And so the key takeaway here is that white light that comes from the sun, it is actually composed of all of these different nice, what we call continuous spectrum light. That's the same as white light. Okay, so we need to contrast that against a different observation that scientists made 150 years ago. So what scientists did, a century or so ago, was they took a pure element, typically a gas like hydrogen, and that's what's being shown in this figure over here. They took pure hydrogen and they put it inside of this tube that would be really the same sort of principle as neon lights that you would see in a downtown restaurant or bar. So they charged it with a whole bunch of hydrogen gas, low pressure. They put some electrodes here, and then they plugged this into the wall. Essentially applied 100 or 200 volts across this thing, and what they saw was this thing would glow. Right? That's essentially this idea of neon lights. Except we're not using neon gas, we're using hydrogen gas. So they constructed these long time ago. And what they did was they did this experiment. Essentially, they put a prism in front of, it doesn't matter that there's a slit here, they put this prism in front of the hydrogen gas discharge tube, and they observed what colors of light were created. And so we just talked about that if you do this with sunlight, or what we consider white or full spectrum light, what we get is a nice continuous broadband spectrum of all the different shades of color that make up that white light. Right? That's sort of what we're used to thinking about. This rainbow that's continuous across the Roy G. Biv spectrum. But what they found with elements, specifically with hydrogen to start with, was that they didn't get this continuous spectrum. So what you're seeing here is a recording film. This is what is being produced, but this section here is just sort of a duplicate of that, showing you that actually what you observe if you do this experiment, and I would do this for you if you were in class with me. I'll show you a YouTube video here in a second. If you actually do this, what you see are these 4 distinct colored lines at these very specific wavelengths. But you don't see anything in between. All you see is blackness, right? Imagine this is the rainbow that you see in your sky during a thunderstorm. Instead of this nice Roy G. Biv, what you get are these tiny bands of light, everything else black. So it's this incomplete rainbow spectrum where all you get are these tiny little bands. So this is a huge clue, right? Chemists and physicists 100 years ago said, this is crazy, right? There's something going on inside of this hydrogen molecule that's giving rise to this. And as you can imagine, we're getting to the electronic structure. How are the electrons arranged in this molecule? And this is the basis of spectroscopy. So let me show you a video here really quick. All right, so what we've got here is a video of an actual hydrogen gas discharge tube. So that's here. So this is like a neon tube that's plugged into the wall. And then to the right of it is a projection of the colors that you actually would see if you were to look at this through a spectroscope that broke the light, or a prism. So what you see if you look directly at the tube is this sort of pink glow, but that pink glow is actually a composition of those 4 distinct lines that I showed you before, all of which are here. And so instead of seeing this nice continuous spectrum like a rainbow, we get these really distinct bands. And what scientists learned about these bands is that this sort of pattern of where the lines showed up and how many lines showed up, that was unique to every single element on the periodic table. So scientists came in and they built a bunch of different gas discharge tubes like this with different elements, and they found out that the colors were all completely different. And so they said that the atomic line spectra, they call them atomic line spectra because they're atoms and they're being excited inside of this tube and they're producing these lines, distinct lines instead of a continuous spectrum. Those atomic line spectra are unique to that particular element or atom. So I'm showing you here a couple different versions of that. So the line spectrum for sodium is here. So you've got these 2 yellow bands, but that's it. So totally different than hydrogen. In sodium, the actual emission looks like this, the image on the far right. We've got neon, which is what early neon lamps were made out of, though modern lamps are made of mixtures of all sorts of different gases to give you the different colors. So we've got the neon gas here, and then we've got hydrogen gas here. And you can see that the patterns that they produce, their line spectra, are completely unique. And so this got chemists and scientists, physicists thinking 100 years ago. They were like, well, why aren't we just getting a nice broadband spectrum, right? We excite these molecules in this tube, in these gas discharge tubes, or we put them into a flame. Either way, it's the same idea that we're exciting them. And the idea is that the electrons inside of those atoms are moving to a higher energy state, and then they must be falling back down and they'll emit some light, and those photons. But what this sort of set of experiments implies is that these gaps, these energy jumps, we're exciting electrons by putting in a voltage or heat from a flame, they're not random and they're not continuous. Meaning, when I excite an electron from, say, a state that's right here, I can't just excite it to any random place. I can either keep it here in its starting place, or I can excite it to the next level, but nothing in between. This is sort of the early discussions of what early quantum physics folks were calling this notion of quantized energy levels. And this quantized energy levels just means that these line spectra, or this was the hypothesis at the time, these line spectra, each line is corresponding to a distinct energy level that an electron can be promoted to and then fall back down and emit light. Right? And this makes sense from a law of conservation of energy perspective. If we put energy into a system, that energy has to go somewhere. And in this case, as the energy is lost, it's lost in the form of light or photons. That means that only these distinct energies of light, or these distinct wavelengths of light, can be allowed to emit. That was the early hypothesis based on these data. Another way to put that is to really think about it in terms of a stairway. And so what these early quantum physicists were thinking based on this data is that electrons can't just start down here and go up to any individual level they want as they're traversing from low energy to high energy. Instead, they're relegated to these discrete steps. And electron can only exist at those steps and nowhere in between. That's this idea of quantized energy levels, as a stairway rather than a ramp. And this was pretty pivotal in the early understanding of electronic structure in an atom. And it all came from spectroscopy and sort of measuring light through the interaction of energy and matter. So that gave rise to one of the early models of the atom, and this was generated by this guy Niels Bohr. It doesn't matter if you remember his name, but more sort of the early thoughts, because a lot of how we think about atoms comes from this. This isn't exactly right, but this was a really interesting step in the right direction. So Niels Bohr came along and he said, okay, well, if you know, energy in an atom is actually quantized, meaning you know, it's sort of this stair step of energy rather than this continuous ramp like we just talked about. He then said, well, you know, if an atom has a bunch of electrons in it, maybe what that really means is that the electrons are sitting in these orbits that are denoted in this sort of figure here, where electrons are a certain distance away and they're oscillating in these orbits, very similar to how physicists and astronomers had thought about stars and planets up at this point. And so he said, well, the nucleus is this black dot in the center, and that's, we already know from early experiments that we talked about in chapter 2, that's where all the mass lies. But the electrons may be free to just zip around in these orbits, sort of like outer space. And the actual distance that the electron exists away in these orbits, he called n. And n is really just the energy level or the orbit level where that electron could move. So if you have electrons that are zipping around in these orbits, and then all of a sudden you apply some energy to this system, to whatever this atom is, by sticking it in a gas discharge tube or putting it in a flame, those electrons go from wherever they started out to a higher orbit. They can't go anywhere in between, right? That's this stair-step idea. They go all the way out to a further orbit, depending on how much energy was applied. And now that electron has the option to fall back down to different energy levels. And this is what Bohr used to sort of rationalize the atomic line spectra. He said that the electron out here, it could fall all the way back down to the n equals 1 category. An electron could fall, so in that case that would be this line, so it could fall from out here in this orbit to the n equals 1 orbit. It could fall from this n equals 5 all the way to 4, from 4 to 1, etc. And he said that that corresponded to the different energy levels of the different photons that were being emitted. And so the picture to the right takes your head some mental gymnastics here for the first time seeing this. But you can think about this. The distance this thing falls from higher orbit energy to lower corresponds to the energy of the photon that gets emitted, or the frequency. And what he said is that, well, electrons, if this is sort of the ground state, and by ground state I mean the atom and the electrons in the state when no energy is applied, if we apply energy, these electrons could fall from up here or any one of these orbits all the way back down. And each time they fall back down, they emit a photon of a characteristic wavelength. And if we look at that in terms of a line spectra, we get these lines that correspond with each one of these bands. And it turned out that his rationale like this pretty well explained hydrogen gas in a discharge tube. And so hydrogen, if you heated it up or you put it in a discharge tube, you would end up getting these little bands from this sort of prediction, or this green set, or this red set that that corresponded pretty well with experiments. So this was a really big first step, just thinking about electrons in orbits and photons and the energy of photons or light, or the color of light, being proportional to how far those electrons fall from excited orbits. That's really the basis of what we call the Bohr model, Bohr, B-O-H-R, of the atom. So this is the Bohr model.